All right, this is one of the last sections in this chapter. This is section 8 out of the text, molecular effusion and diffusion. Similar processes, but different. So two consequences of the dependence of molecular speeds on mass. Remember, the lighter the mass, the faster the molecule. Effusion is the escape of gas molecules through a tiny hole into an evacuated space. Okay, that's effusion. The best analogy, like it's hard to think of a everyday situation where effusion occurs. If you were to pass gas in the vacuum of space, that would be effusion. Okay, the escape of gas molecules through a tiny hole into an evacuated space. Now, diffusion, on the other hand, happens all the time. The diffusion is simply the spread of one substance throughout a space or throughout a second substance. So, anytime you spray perfume or air freshener, you're witnessing or sensing diffusion, the way the molecules just move around quite quickly, actually, until they fill their container or the room. Oops. Okay, so here it is visually. Diffusion is just if we were to have a partition here and have a bunch of gas on this side, and then we remove the partition, almost immediately the gas has spread out and filled the entire space. Here's effusion if we have a partition that's keeping the gas completely separated from this other side. And fusion happens obviously a little slower because all the gas molecules have to pass through this little hole here, but they will effuse until there's equal amounts of gas molecules on each side of the partition. You can figure out the rate of diffusion and effusion with the right algebra formula. The thing to remember, though, is even without calculating anything, the lighter the molecule, the faster it moves, so the faster it diffuses and the faster it effuses. All right, so here, this is Graham's law of effusion, so yet another law. Okay, the effusion rate of a gas is inversely proportional to the square root of its molar mass. In English, okay, the lighter they are, the faster they go. Gases effuse through the pores of a balloon. Okay, at identical pressure and temperature, the lighter gas is going to effuse more rapidly. So, if you've ever had a a helium-filled latex balloon, you know it's not good for very long. Okay, so here in this example, they have nitrogen and helium in these two separate balloons, same volume and same temperature. The nitrogen's not floating because it's more dense than air, whereas the helium's less dense, so it is floating. And over time, gases escape out of the pores of the balloon. Helium is quite a bit lighter than nitrogen. Nitrogen, for example, a mole of N2 would be 28 grams, whereas helium's only 4 grams per mole. So the helium is going to effuse much quicker and exit the balloon than the nitrogen. So the heavier they are, the slower they move, and the slower they effuse or diffuse. Okay. So arrange the gases according to increasing molecular speed. So when I say increasing molecular speed, I mean to start with the slowest one and work your way up to the fastest. Okay. So we've got helium at 25 degrees, helium at 100 degrees, and neon at 25 degrees and neon at 0 degrees. So who's going to be the slowest? Okay, the molar mass of helium is 4 and neon is 20. This is going to be embarrassing if I'm wrong, but I'm pretty sure it's 20. So neon is the heavier of the two, so it's going to go first, but which neon? Is it going to be the 0 degree neon or the 25 degree? Okay, we want the slowest one. So the coldest is going to be going the slowest. So temperature and mass determine their speed. So neon's the slowest. Neon at 0 degrees, really cold neon, is going to be moving the slowest. So that pretty much gets us to the answer already, because the next step is still going to be neon moving the slowest because it is the heaviest. It's just neon at room temperature at 25 degrees Celsius is going to be going a wee bit faster. Then we have the colder helium. We have helium at room temp and then at 100 degrees Celsius. And so the fastest molecule of them all will be the lightest and the hottest, the helium at 100 degrees. All right, now this is, I don't know why, one of my favorite sections in this chapter. I don't know what it is about it that I enjoy so much. So basically, theories, as I have said a million times throughout the course of biology in this class, theories are just scientists' attempt at explaining why things are the way they are. Okay, so we have all these gas laws that state the obvious. Okay, when gases are heated up, they expand, so their volume increases. The lighter they are, the faster they travel, etc., etc. We've got all these gas laws. So the kinetic molecular theory is our attempt at explaining why. But you may have noticed so far that in the gas laws, we don't have to account for what gas it is we're talking about. We don't have to worry about whether it's nitrogen or helium. All the gases are assumed to behave the same. And you know what happens when we make assumptions? So we make some assumptions in the kinetic molecular theory that aren't actually true. Okay? So the assumptions in KMT show where ideal gas behavior breaks down. Okay, we make some assumptions, and most gases follow those laws at sane temperatures and pressures. Okay, but things start to break down. Okay, first of all, we assume that it doesn't matter how big a gas molecule is. Obviously, a Cl2 molecule is going to be a lot bigger than a H2 molecule. But we assume that the gases are so small in comparison to the volume of the container that they're in that their size is irrelevant. But the molecules do actually have a finite, quantifiable volume. So that's one assumption we make that isn't true. And we also assume that the gases are so far apart and traveling so fast that they never have a chance to attract to each other. Well, they do actually attract to each other. So these first two right there mess up two of our gas characteristics. The fact that the molecules do have a finite volume means that they are taking up possibly a significant amount of space in the container, so that affects our V. Molecules attracting to each other, well, think about it. If all of a sudden the O2 molecules in the gas started attracting each other quite a bit, well, if they're pulling towards each other, then they're not going to be bouncing into the walls of the container as much, and that's going to cause the pressure to decrease. So this is why in real life, gases under certain conditions deviate quite a bit from ideal gas behavior, meaning PervNERT does not give us the exact perfect right answer all the time, okay, because of some assumptions that we make. Okay, so the model of gas behavior, that they don't attract each other and that their size is negligible, falls apart at high pressure and at low temperature. Okay, and here's why. If you have a gas at a high pressure, that means you've squeezed it into a small little space, and so your molecules are real close together. Well, the bigger your molecules are, the more of that space they take up. Okay, so your volume isn't really a half a liter. It's less than that because the molecules themselves are taking some of that half a liter space up. Okay, then at low temperatures, the gas molecules aren't traveling very fast, and so the slower they're going, the more likely they are to be able to attract one another. Okay, so when they're bouncing around slowly, when this guy bounces, okay, he's gonna be close to these guys. If the pressure's high enough, he's going to be close to the other molecules. And if he's moving slow enough, he's not going to be able to overcome the attraction he has for the nearby molecules. And that would cause the pressure to not be accurate. The pressure we get with the ideal gas law anyway. Okay, so as the pressure on a gas increases, the molecules are forced closer together, and as they get closer together, the free space in which they can move gets smaller, leading to more attraction. So the smaller the container, the more of the total space the gas molecules occupy. So a small container, high pressure, the less space there is between the molecules, and the slower they're going, the more attraction there is between the molecules. So all that comes together and makes PV equals nRT not work too great. So therefore, at high pressure and at higher pressures and lower temperatures, there's a fruit fly buzzing around me, sorry. The less the gas resembles an ideal gas. The higher the pressure and the lower the temperature, the less the gas follows PV equals nRT. So as the gas molecules get closer together, the distance between the molecules decrease. Good. Okay, Daddy went to get, oh boy. Anywho, where was I? The higher the pressure, the less the gas resembles an ideal gas. And as the molecules get squeezed closer together at that higher pressure, the intermolecular distances between the molecules decreases. And the smaller the distance between the molecules, the more attractive forces they will have on one another. Therefore, the less the gas resembles an ideal gas. So there's two reasons. It's because of the volume of the gas molecules themselves, their size, which varies from gas to gas, and the temperature of the gas. That can make a gas not follow PV equals nRT. All right, now, as you increase the temperature and get the gas hotter, the molecules move faster and get further apart. There's more energy to break free of those intermolecular forces. And so as the temperature increases, the negative departure from the ideal gas behavior disappears. How do you like that wording? The negative departure from the ideal gas behavior disappears. Okay, at higher temperatures, PV equals nRT works better, is what that says. Okay, so is water vapor more or less dense than nitrogen under the same conditions of T and P? Okay, this is kind of a random question. So we're looking at water vapor, so H2O gas, and nitrogen gas at the same temperature and pressure. So our choices are densities cannot be compared without additional amount and volume information, or water vapor has the same density as nitrogen under the same conditions of temperature and pressure, or water vapor is less dense than nitrogen, or water vapor is more dense than nitrogen. Okay, water vapor is less dense than nitrogen at the same temperature and pressure. If you think of the molar mass equals dRT over P equation, we're assuming the same T, the same P, R is always the same thing. So that leaves us with molar mass and density. Okay, so there is a relationship between molar mass and density here. So if we have the same temperature and pressure and same volume even, the density is going to be due to the difference in mass. And water vapor is 18 grams per mole, whereas nitrogen is 28 grams per mole. So it's going to be more dense if we have them in identical conditions. Okay, real gases deviate from ideal behavior at blank and blank. So real gases stop behaving ideally at which conditions? High temp and low pressure, low temp and high pressure, high temp and high pressure, or low temp and low pressure. Okay, what causes PV equals nRT to not work? Low temperatures, because the gas molecules slow way down, and high pressures, because the molecules are squeezed so close together, they do start to attract each other. All right, so here is a graph of PV over RT for various gases. Okay, and this is what an ideal gas would be like, but you can see as the temperature goes up, the deviation from the ideal gas law isn't as bad. Okay, the hotter the gas, okay, the closer it is to behaving ideally. The colder it is, the further it's from it. And then, also, oops, wrong button, pressure. As the pressure decreases, okay, do what? Yeah, you can. Okay, consider 3 samples of gas, HCl, hydrogen, and oxygen. at different temperatures. Compare the average kinetic energies in these three samples. Well, kinetic energy